Hello everyone, welcome back, and you are watching DMG chemistry classes. And in today's video I am going to explain the law of conservation of mass and energy. In my previous video I discussed the law of conservation of energy, which is also called as first law of thermodynamics, and it states that energy can neither be created nor destroyed, although it can be converted from one form to another. But in 1905 Einstein showed that mass can be converted into energy, and he showed that E is equal to mc square. This equation can also be interpreted that mass and energy are interconvertible. Means that mass can be converted into energy and energy can be converted into mass. Okay, then we have to redefine the law of conservation of energy, and it will be defined in a way that the total mass and energy of an isolated system remains constant. And I have explained in my previous video what is isolated system here. The entire universe can be considered as an isolated system. Okay, now let us explain this law of conservation of mass and energy. And to explain this, I have taken the example of carbon atom. Okay, and we know that carbon atom is composed of 6 protons, 6 neutrons and 6 electrons. These 6 protons and 6 neutrons are present inside the nucleus, and whereas 6 electrons are revolving around the nucleus, 2 electrons are revolving in the first main energy shell and 4 electrons are revolving in the second main energy shell. And now let us suppose that we disintegrate this carbon atom. We decompose this carbon atom into its constituent subatomic particles by supplying some energy. Okay, हम इस कार्बन एटम को तोड़ देंगे किसमें, इसके subatomic particles में, by supplying some energy. So now here we will have 6 protons, 6 neutrons and 6 electrons. Okay, then we will calculate the total mass of these subatomic particles by adding mass of the 6 protons, 6 neutrons and 6 electrons. And the total mass of these subatomic particles comes out to be 12.11 AMU. Okay, and we know that the atomic mass of the carbon atom is 12 AMU, atomic mass units. So at first sight it seems that law of conservation of mass is not valid here, because the mass is different on both the side. In this side we have 12 AMU and here we have 12.11 AMU. So what does it mean? It means that mass is not constant or conserved, but this is not the case. Here mass is also conserved and energy is also conserved. Let us explain how. Here the mass has increased by amount 0.11 AMU. Okay, and from where this 0.11 AMU has come? Okay, here the energy which is supplied to disintegrate this carbon atom has been converted into mass. Okay, this energy has been converted into mass, and how much mass? 0.11 AMU. Okay, so here also we have 12 AMU mass plus additional 0.11 mass is due to the conversion of energy into mass. So in this way energy is also conserved here in the form of mass, and mass is also constant. Have you understood? So now let us reverse this process. Now what we will do, we will reconstitute the carbon atom from its constituents subatomic particles. That is, the 6 proton, 6 neutron and 6 electron, they are again forming the carbon atom and energy is released. Okay, and as I told that the total mass of these subatomic particle is equal to 12.11 AMU, and here the mass of the carbon atom is 12 AMU. So here also it seems that mass is not constant on both the sides. But actually mass is constant. How it is constant? Because here we have 12.11 AMU. So this 0.11 AMU mass has been converted into energy. Okay, so here this 0.11 mass is present in the form of energy. So total mass will be 12.11. Understood? So in this process, mass and energy or total mass of the energy is remaining constant. Understood? Now this equation E is equal to mc square is very important in nuclear reactions, because in nuclear reactions mass of the product is less than the mass of the reactants, and that loss in mass is converted into huge amount of energy, because this mass is multiplied by c square. C is the velocity of light, and we are going to get more amount of energy during nuclear reactions. But as far as ordinary chemical reactions are concerned, ordinary chemical reaction, I mean to say the reactions which are not nuclear. A simple reaction is like this HCl plus NaOH giving us NaCl plus water, okay, or carbon plus oxygen giving us CO2. So these are the ordinary chemical reactions, and in these reactions mass remains constant. Okay, there is no significant change in mass. Mass remains almost constant, and if there is any change in mass, that change will be infinitesimally small change and can be neglected. So in these ordinary chemical reactions mass remains constant. And why the mass remain constant? Because in these reactions nuclei of the atoms remains intact. Nuclei of the atom mean to say nuclei of hydrogen, chlorine, sodium, nuclei of all atoms remain intact. And when the nucleus is intact, mass is intact, mass is constant, because we know the definition of nucleus. Nucleus is the center of the atom where the entire mass and the entire positive charge is concentrated. So in these reactions, ordinary chemical reactions, mass remains constant because nucleus remains intact. Whereas in nuclear reactions, the nuclei of the reactants are not intact, because those nuclei are bombarded with what? Projectiles like neutrons, like protons, alpha rays, beta rays. So changes take place in the nuclei of the atoms, and when the changes are there in nucleus, then there will be change in mass. Okay, so in nuclear reactions there will be a change in mass. Product will have less mass than the reactant, and the loss in mass, which is also called as mass defect, will be converted into energy according to this equation. Understanding or not? I can write a nuclear reaction for you. For example, this is uranium 235 and I bombard it with neutrons, and what I get? I get barium, krypton, and 3 neutrons. So in these reactions, this neutron is a projectile. It bombards the nucleus of uranium. So changes occurs in the nucleus. Okay, and resulting elements are barium and krypton. So there will be a difference in mass. Mass of the products will be less than the mass of the reactants. Okay, so this equation, that E is equal to mc square, is important or significant in case of nuclear reactions. So this law of conservation of mass and energy is also important in case of nuclear reaction, because in nuclear reactions mass is converted to energy. Whereas in ordinary chemical reactions, okay, mass is constant. Okay, so for ordinary chemical reaction we require only what? Law of conservation of energy. And in thermodynamics we deal with what? Ordinary chemical reactions, ordinary processes, or the macroscopic properties. Nuclear reactions are not studied in the chemical thermodynamics. Okay, so that's why we will concentrate only upon what? Law of conservation of energy in chemical thermodynamics. Okay, so this was all about law of conservation of mass and energy. And in my next video I am going to discuss the mathematical formulation of first law of thermodynamics, a very important topic. So keep watching my videos and please like and share my videos and also subscribe my channel. Thank you very much.